The previous video, lecture 12, we looked at plane wave incident from a dielectric region hitting onto a PEC boundary. Today what we look at is a wave propagating in pure dielectric, lossless dielectric medium, going on to hitting another dielectric medium, which is again lossless. Again, normal incidence is what we are considering. A quick recap, you are familiar now, and tau is that, gamma is this. We are familiar with all these equations, we understand the notation. Good. We want to evaluate tau and gamma and understand the behavior of EI, ER and ET. Correct. That's the. Okay, let us take dielectric to dielectric interface. Region 1 is a lossless dielectric, sigma 1 equal to 0. Region 2 is also a lossless dielectric, sigma 2 is equal to 0. And we want to evaluate eta 1 and eta 2. Since sigma is 0, eta 1, eta 2, both of them are purely real and given by eta naught upon the square root of respective relative permittivity. Eta naught is the intrinsic impedance of free space, 376.73 ohms. Now if I substitute the value of eta 1, eta 2, it is not very difficult to show that tau is given by this equation and gamma is given by this equation. Nothing exotic happening here, it's just an equation, helpful. What it implies is that if epsilon r2 is greater than epsilon r1, gamma is minus 1, and if epsilon r1 is greater than epsilon r2, it is gamma is plus 1. That's all that's going to be conveyed here. What is interesting is are the fields. If I can evaluate EI and HI. We know these two, EI, HI. So SI is the power associated with the incident wave. We had done this before, is 1 by 2 eta 1 AZ cap E naught square propagating in Z direction. Good. How about the reflected wave? Oh, we had done that before, but in the previous situation, we had chosen gamma as minus 1. This time we will not choose it as minus 1, we will keep it as gamma itself. And therefore, SR will be ER cross HR star, and AX cross AY will give me AZ, gamma star will be gamma square, and E naught star will give me E naught square, and e to the power of j beta 1 Z and minus j beta 1 Z, they will give me a unity. And if you notice here, this power is propagating in the negative Z direction. Perfect. That's what we wanted. Exactly the same approach for calculating the power associated with the transmitted wave. Write the equation for ET, HT. We know that. This is straightforward, right? Now take ST, half of real part of ET cross HT star, and straight away you can simplify it as 1 upon 2 eta 2 AZ cap tau square E naught square. Brilliant. So we have power associated with the incident field, and incident wave, reflected wave and transmitted wave. Let's calculate the total field. So we know EI, HI, incident fields, ER, HR, reflected fields, ET, HT, transmitted fields of the waves. Yeah, that's perfectly fine. So what is E1? It is a total electric field in region 1, which is equal to EI plus ER. So just add them up. Similarly, H1 is HI plus HR, add them up. Now, what is the power in the fields in region 1? E cross H star, or rather E1 cross H1 star, which you can straight away see that AX cross AY will give me AZ cap, and 1 upon eta 1 remains as 1 upon eta 1, and E naught star will give me mod E naught square. Then you have a real part of the first quantity, the bracket quantity in the bracket of electric field multiplied by the quantity in brackets of the magnetic field complex conjugate of it. Now if you expand this, you get e to the power of minus j beta 1 z multiplied by e to the power of plus j beta 1 z because of complex conjugate. Then you get 1 e to the power of minus j beta 1 z, or let's take this gamma e to the power of j beta 1 z multiplied by e to the power of j beta 1 z gives me gamma e to the power of 2 beta 1 z with j, of course. Then we have gamma star times e to the power of minus j 2 beta 1 z, and the last one, gamma times gamma star gives me gamma square, and j beta 1 z and minus j beta 1 z, it will become unity. We are trying to take the real part of this. 1 is a real quantity, gamma star mod is a real quantity, but we have two terms in the middle. One, if you think of it as a complex quantity, say A, the second term is a complex conjugate of that quantity A. That is, A minus A star is always purely imaginary. A plus A star is purely real, A minus A star is purely imaginary. Therefore, the real part of this will be nothing but Az cap E naught square times 1 minus mod gamma square. Hey, this is very interesting. The total power that is associated with region 1 is Az E naught square upon 2 eta 1 times 1, which is the incident power, minus gamma square times that, which happens to be the power associated with the reflected wave. Therefore, the total power is whatever is incident minus whatever is going back. Such a relationship will be valid only if there is some orthogonality conditions maintained between the incident and reflected fields. That is, if you have some electric plane wave with some electric field E1, and if you have another plane wave with some electric field E2, each having powers P1 and P2, the total power associated will be equal to P1 plus P2 only if E and H fields E1 and E2, H1, H2 are orthogonal to each other. If they are not orthogonal to each other, then total power will not be equal to P1 plus P2. Then the only way you can compute the total power is calculate EI or E1 plus E2, H1 plus H2, and then take the cross product. Superposition of power is not always valid, whereas superposition of fields is always valid. So you should be little careful. My suggestion is, when you are in doubt, make sure you use superposition of field concept and don't simply add powers. To plot the fields, we follow the exact approach that we had followed before. Take the electric and magnetic field in the phasor form. In this particular case, total electric field E1 and total magnetic field H1, and write it in the time harmonic form. How do you do that? You multiply this quantity by e to the power of j omega t and take the real part of it for both E and H. And we are ready to plot this. This is how the plot is going to look like. This is at a particular instance of time as a function of z. The top picture gives the electric field, the bottom picture gives the magnetic field. Notice that this is the x component of the electric and y component of magnetic field, and both of them are tangential to the surface. Therefore, both electric and magnetic fields must be continuous, and you can see that continuity here very clearly. The fields are equal in region 1 and region 2. Both the electric fields are equal as well as magnetic fields are equal. You can also observe something here. The wavelength is different in two regions. That is because we have chosen two different values of permittivity. If you spend a little bit time, if you can even estimate what is the value of permittivity from this picture. But what I'm interested today in showing to you is how this particular fields will change or move or vary as a function of time. So we'll make a movie of that. If you notice here, there is some component which is going forward and there is some component going up and down. See this, if you notice, the red trace can touch a maximum somewhere here and will touch a minimum here. It will never come down below that. Do you want to watch that again? Yes, we'll go back and now watch this carefully. I'm going to move slowly. It touches the peak, comes down, and it never goes below that, and then again it goes up, and again it comes down, never goes below that, again it goes up, and so on. And if you see that the electric field will never cross an envelope given by that gray trace there, and that gray trace represents the standing wave pattern. If I were to take a probe, we'll talk about probe, we'll see how it is done in electromagnetic theory later on in the course. If I were to take a probe and then were to measure the electric field and I measure it along the distance z, then what I'll see is a pattern which is shown by the gray trace there, which will have a maximum and it will have a minimum. If the minimum goes to 0, then it is pure standing wave. maximum will not go to infinity. Maximum will go to a maximum value of 2 times E naught when gamma is equal to +1 or -1. Now let's try to understand this picture a little better. We have a quantity called E max and a quantity called E min. Ratio of E max to E min is known as the standing wave ratio. Are you familiar with this? Yes, you must be. You must have come across this in transmission lines and in other courses as well. It's exactly the same standing wave ratio. If it were to be a standing, transmission line standing if it were to be a transmission line, we would have called it as voltage standing wave ratio or current standing wave ratio. Here we just refer it to as SWR, and whenever we say SWR without any prefix, then it refers to the ratio of the electric fields. Okay, finally we will establish a relationship between the reflection coefficient and standing wave ratio. Are you aware of this? Of course you are aware of it. There's nothing new in this. But we'll just finish it. We'll just complete this task. SWR is Emax upon Emin. What is the electric field? E incident EI plus reflected ER. And Z represents the distance in the space coordinate system. If I were to choose a new coordinate system called L, which is equal to 0 at the discontinuity, and it is positive towards the source, towards the left part, then L will be equal to -Z. Therefore, E1 magnitude is equal to E naught times 1 plus gamma e to the power of -j2 beta 1 L. How did we get this result? It's very easy. You take out e to the power of -j beta 1 Z. When you take the magnitude, it is equal to 1, and what is left is 1 plus gamma times e to the power of j2 beta 1 Z, and we replace that Z by -L to get this result. Let us plot this and see what happens. To plot this, we'll take that complex plane, Argand diagram, real axis on the horizontal, imaginary vertical. Then we plot 1 plus j0, which represents that 1 in the electric field, and we want to plot this gamma e to the power of -j2 beta L. That we will write it as mod gamma times e to the power of j psi, where psi represents the phase angle of gamma, and we have -j2 beta 1 L sitting there. Therefore, I'm going to plot a vector of length mod gamma and making a phase angle psi minus 2 beta 1 L with respect to the real axis. Okay, then what is 1 plus gamma e to the power of -j2 beta 1 L? It is that quantity, that red arrow there on the screen. Now, what happens when L changes? L equal to 0, psi is 0. As L increases, this quantity keeps decreasing, and in complex notation, decrease means it is going in the clockwise direction. So when it goes in the clockwise direction, it cuts the real axis twice. In one point, that is on the rightmost point, the value of 1 plus gamma e to the power of -j2 beta 1 L will be a maximum, and on the leftmost point, it will be minimum. Rightmost point corresponds to Emax, where the magnitude is 1 plus mod gamma, and the leftmost point will be 1 minus mod gamma. Therefore, SWR is 1 plus mod gamma upon 1 minus mod gamma. So, this is the point where I want to convey once again the similarity between plane wave normal incident on a dielectric or PEC interface and transmission lines. Electric and magnetic fields can be thought of as voltage and current on a transmission line. All the techniques used in transmission lines are applicable to solve problems here. Yes, even Smith chart. We can use Smith chart to solve problem, very handy and a powerful tool. Probably in the assignment, I'll give you 1 or 2 examples where I'll motivate you to use Smith chart, and you'll realize that all those principles can be used to solve electromagnetic wave problem when you are considering a plane wave incident normally onto an interface.